prisoners of our cosmic crater. I apologize for the pronunciation and for any mistakes, but given the great confusion and the ignorance there is about this subject, I am motivated to publish it. General relativity says that the universe is like an immense, flat and undulating net. Each object that falls on it sinks, forming a crater that descends in depth according to its mass. Big mass, big crater. Small mass, small crater. Our cosmic crater is relative to the mass of the Sun, and this means that it is enough big to keep us prisoners in its hole. In other words, we can't get out of this crater. We are born, live, and die in it. In spite of this, there are scientists who talk about spaceships that could travel from one planet to another, from one star to another, from one galaxy to another. Others that we can travel in a black hole and arrive in another universe and start a new life there, occupying, hopefully, the most peaceful and beautiful planet. Instead, those who are eager to know everything in a cosmic level can do it in a short time, traveling in wormholes between one world and another. Then there are those who say that, with ion-powered spaceships, we could navigate around the universe and enjoy ourselves stopping here to get some sun, suntan, and there to refresh before resuming our journey. All this and much more, is it possible? Not at all, says categorically Alan Cromer, and explain this space business in a totally different way. Here is what he says about space in his book, Uncommon Sins, The Heretical Nature of Science. Cromer writes, the star of Barnard, that is in the Alpha Centauri, 6 light years from us, is the closest star to the Earth that can maintain a stable planetary system. Indeed, there is some indication that it may have at least one planet the size of Jupiter. Let's see how long it would take a Barnardian to reach the Earth. The Earth is 6 light years away, or 57 billion kilometers from the star of Barnard. It is only a matter of arithmetic to calculate the speed that a Barnardian spaceship would need to reach the Earth at a given time. For example, if the journey is 60 years, the speed should be approximately 1/10 of that of light, or about 30 6,000 kilometers per second. For a journey of 600 years, the speed should be 1/100th of that of light, that is 3,000 kilometers per second. And for a journey of 6,000 years, this speed should be 1,000th of that of light, or 300 kilometers per second. The most fundamental physical law of all tells us that the only way a spacecraft can increase or decrease its speed in a vacuum is by shooting off matter in a high speed. Now, let's suppose that the Barnardians are patient people, eager to travel for 6,000 years in order to fill the front pages of popular newspapers. Now, for being able to land softly on Earth, their spaceship should slow down from a speed of 300 kilometers per second to the speed of the Earth's rotation around the Sun, about 31 kilometers per second, turning on its engines on the opposite side of its direction. The amount of matter that the spaceship must be able to expel depends on its weight and on the propellant's discharge speed. For example, a 50-ton spacecraft, the size of what took the Apollo astronauts to the moon, would have to expel more than 50,000 billion tons of matter at a speed of 10 kilometers per second. This means that a small 50 tons Barnardian spacecraft should reach our solar system connected to a 5-kilometer wide and 1.5 kilometers long fuel tank. For throwing such a monster, the Barnardians would need a rocket bigger than their own planet. All this to send a spacecraft large enough only to accommodate 3 human beings on a one-way trip to the Earth of 6,000 years. The main difficulty with space travel is that a vehicle must carry all the fuel it will need, both to increase and to decrease its speed. There are no filling stations in space, but the larger the vehicle tank, the greater the total mass that must be accelerated. It's a vicious cycle. More fuel is needed to go faster, but the increase in fuel quantity adds weight to the vehicle, making further speeding more difficult. Consequently, even with larger tanks, the final speed increase remains small. Would things change if we imagined some new futuristic fuel? No, because the fundamental element of the propellant of a rocket is the speed with which it moves away from the rocket itself. In a chemical propellant rocket, this speed depends on the temperature at which the propellant burns and how small the atomic weight of the basic element of the propellant is. There is a maximum temperature, the melting point of the metal. In addition to this, one cannot go. On a journey from a Barnard star to the Earth, an ion-propelled spaceship should accelerate for thousands of years before reaching the speed of a chemical rocket. At this point, it would be halfway to the Earth and should begin to reverse the thrust of the engines, still taking several thousand years to slow down at the speed of the Earth's orbit. Throughout its journey, which could last from 5 to 10,000 years, all of the ship's machinery should function perfectly. In this last time, there was talk of another space navigation system, sailing space ships. This idea is beautiful, even romantic, but is it realistic? The dangers encountered in the open space are infinite. The idea that spaceships can one day wander from star to star is great for science fiction, not for science. The laws of physics and the properties of matter limit the speed of spacecraft, making interstellar travel impossible in a reasonable time. This conclusion is surprisingly unpopular. Instead of feeling relieved, knowing that we cannot be invaded by hostile aliens, people are troubled by the idea that our technology is approaching some theoretical limit. Sure, people think if the technology has managed to take us from 5 to 40,000 kilometers per hour, 11 kilometers per second, in just 160 years, one day speed in excess of 300 kilometers per second should be possible. Technology doesn't work in this way. Human experience shows us that new technologies soon reach the limit of their development. The Pyramid of Cheops was built in 2680 BC, only a few hundred years after the Egyptians learned to cut and move large blocks of stone. They continued to build pyramids for another 1,000 years, but they never built one so large. Men landed on the moon only 8 years after Yuri Gagarin's forced orbital flight. The landing on the moon could be our pyramid of Cheops, a result destined to be no longer overcome. Although a human mission on Mars is technologically possible, it is not certain that it would be compensated by its costs and by its risks, concludes Alan Cromer. At this point, I ask myself, if the space road to Mars is so full of thorns and dangers, the idea to go beyond Neptune and deep into the cosmos is a part of our dreams, not of our real possibilities and of our real good sins. Our reality on this planet is that we are, like it or not, its prisoners. We are like bees. Bees are born, live and die in their hive. We human beings are born, live and die in our cosmic crater. This fact should have taught us to learn how to love our crater, that is our house, our nest, our everything, and to try to live in it as much as we could and as good as we can. Instead, it is not so. Instead, we do the opposite. In fact, we waste most of our energies and of our life dreaming and doing foolish things. Why? Why we behave so irrationally? Why do we have to be always looking for the impossible when this turns out to be negative and catastrophic? Are we human beings, so hopelessly absurd and irremediable? The problem, in my opinion, is simple and yet of a big tragic dimension. The problem is that we have not yet learned how to live in harmony with our world and become not an alienated part of it, but a real balanced and constructive whole with it.